Okay, so welcome everybody to our today's Café Scientifique webinar. I have the pleasure to be the moderator. I have to say I was originally asked whether I could present on this topic, but then I said, no, I think that would be much better if Nico would do it, because Nico was a PhD student who just graduated this year, and I think he was extremely talented to measure over 130 compounds, internal concentration, and develop protocols for this. And I think he deserves actually also to present the data. So what I'm doing is I'm just moderating and I'm giving a small teaser. I apologize for the people that had often heard these discussions in PrecisionTox, but I know we have also some other people here, and for this purpose, I would like to give you a very short teaser of a concept, important concept in the background before Nico is talking about the biotransformation of xenobiotics. So you will hear today a lot about a toxicity concept, which is called the baseline toxicity concept. To understand what this means, is that you have to recall that chemicals always interact initially at the molecular level, and that an important molecular initiating event that is kind of inherent to every chemical is the interaction with cellular membrane. So that's kind of the minimal toxicity that a chemical provokes, and this is related to the intercalation of compounds in the membrane, and if they are hydrophobic, of course they intercalate more, and this is contrasted by other unspecific interactions such as reactivity or uncoupling. Uncoupling, for instance, I don't want to say more about this, but these are, for instance, then modalities that typically provoke a higher toxicity than just the intercalation with the membrane. And if we can go to the next slide, please. Then we have also, of course, a specific interaction, meaning that chemicals can bind to certain receptors. And the receptor can be a hormone receptor, an intracellular receptor, it can be an external membrane protein, a transmembrane receptor, but it can also be any kind of protein or structure in the cell that has a specific binding capacity. So typically then these specific interactions, they are stronger often than the baseline toxicity. But the baseline toxicity, which is driven by the hydrophobicity, can be predicted simply by regression, curve, and that's shown in the next slide. This stems back to very early concepts developed in the context of ecotoxicology in the 1992 by someone who was called Fahar, and he noticed that the fish toxicity, the acute fish toxicity, is very much driven by the hydrophobicity for certain type of compounds that are not known to have any specific interactions. But if you have specific interactions, if the compounds are reactive, then you notice that the compounds are much more toxic than by this simple regression. And in order to differentiate this, the term toxic ratio was developed, meaning the more you deviate from the regression line, the higher the toxic ratio is. And this is an indicator of specificity. And that means when you compare your compound effects to this regression, you always have a first indication that a compound has a specific interaction and then maybe also a specific risk. And what I'm showing on the next slide is how this looks like. So there's sometimes a misunderstanding that this does only function or is only working in the aquatic toxicology, but it's valid for all waterborne exposure system, and that means it's also very relevant in the human toxicology field, where NAMs often use cell cultures for the assessment of chemical effects. What you can see here is the regressions of baselines for nematodes, Daphnia, zebrafish, and the generic cell model, and they're all quite similar, which is not surprising because all these models consists of cells, of cell membranes, and there's maybe a little bit of a difference in the percentage of saturated lipids or whatever, but in principle it's the same. And the interesting is that this regression line is based on the external concentration, but if you translate it to the internal concentration, then actually you get the same concentration of all other compounds in the internal membrane, because that's kind of translating into a threshold when this cell membrane function is then disturbed in such a way that the cells die or the organism die, or that it's compromising other function. Here it is compared to the LC50, but there's another possibility that you compare the baseline toxicity to sublethal endpoints to assess the specificity. So the final slide in my little teaser is talking about important factors for the prediction and the calculation of the baseline toxicity. One important thing is dissociation. Some compounds dissociate, and that means they have a neutral form and a charged form, and that has an impact on their hydrophobicity at this given pH. So that's something you have to consider. And what we want to focus today on is the potential impact on metabolic degradation. Because if the internal concentration is reduced by strong metabolic degradation, this means that it may look like as if the compound is baseline or is less toxic, and that you kind of miss potentially the specific interaction. And that was an important aspect in the project that's will now be presented by Nico, why we took the effort to look at 130 or more compounds for the internal concentration, and what we could learn from this event. And I'm very happy and thankful that Nico had the time to present today. So I would like to hand over to Nico.
Yeah. Thank you, Stefan, for the nice introduction. As Stefan already mentioned, I will present you my PhD project on the biotransformation of xenobiotics in zebrafish embryos and its influence on internal concentrations and toxicity. First of all, I would like to give you a very general introduction, but an important introduction. Around 100,000 chemicals are in regular use, such used in personal care products, pharmaceuticals, or compounds used in agriculture, industrial applications, or also road traffic related compounds, resulting in environmental exposure. Many of these chemicals are potentially toxic, where their environmental fate, exposure pathways, and hazard profiles remain poorly understood. That's why we have to assess the risk of these compounds for human and the environment. And to assess the risk, we must consider, on the one hand, the hazard, namely the underlying mechanisms causing toxicity, and on the other hand, the real-world exposure. And when these both factors are overlapping, we speak about the risk. And if we want to make chemical risk assessment, we need first to assess how toxic actually a compound acts to an organism. And currently, we have several limitations in chemical risk assessment. Well, chemical risk assessment is traditionally based on animal testing. At the same time, the number of chemicals in use is rapidly increasing, where these tests remain expensive, time-consuming, and ethically debated. And this creates a growing gap between the need for comprehensive evaluation and our capacity to assess the risk in a timely and systematic way. As a consequence, this gap has driven research activities in establishing alternative test approaches for animal testing, so-called NAMs. And one very important test species used for such alternative strategies is the zebrafish embryo. Why is this attractive for studying NAMs? Well, it combines advantages like its small size, fast development, and reproduction, which increases the throughput of tests. And second, the zebrafish embryos share, for example, homologs for about 86% of key human genes and conserved major biological pathways supporting their use in vertebrate mechanistic toxicology. Third, optical transparency for example, monitoring studies of organ development. And also one important point is that this model avoids ethical restriction because the embryos are not legally protected before 120 hours post-fertilization. However, a major challenge is still to demonstrate full cross-species transferability of data, for example, from zebrafish embryos to mammals or humans. And this is largely because we still lack a complete mechanistic link between the chemical structure, the transformation, and the biological effects. And therefore, a deeper understanding about the interaction of chemicals with the zebrafish embryo or in general with model organisms is essential to evaluate the predictive power of this model approach for chemical risk assessment. And now I come to a very important part, how we can go the step from the exposure to the effect. And this can actually separate it in two basic steps. First one is the toxicokinetic step, and the other processes are summarized in toxicodynamics. What we can see is that in the toxicokinetics, this describes actually what happens to the chemical inside the organism, and toxicodynamics describe what the chemical does to the organism. And toxicokinetics typically include the uptake, the distribution, the biotransformation, and the elimination of the compound, and it modulates actually the internal concentration at the target site. And this is effectively driving a cascade of several biochemical reactions, starting with a molecule initiating event, resulting in a toxic mode of action and the observed toxic effects. And toxicokinetics determine how much of the compound enters the organism, but whether this leads to toxicity depends also strongly on the underlying mode of action. Well, and Stefan already nicely described one very important concept for distinguishing chemical mode of actions is the concept of baseline toxicity. Baseline toxicity is the minimal toxicity caused by non-specific membrane accumulation, and it occurs typically when a critical membrane concentration is reached. And one very important aspect of baseline toxicity is its predictive power, because baseline toxicity is largely driven by non-specific membrane accumulation and therefore strongly related to its hydrophobicity. So there's a linear relationship between toxicity and hydrophobicity. And typically, if we have a specific mode of action, this increases the toxicity compared to the unspecific baseline toxicity. So it's a very important tool to screen compounds for the specificity and mode of actions. And however, the predictive power of this approach is sometimes limited by only relying on external concentrations, but the concentration inside the organism is not considered. Consequently, the external concentration is just a proxy for the biologically effective dose, and this has the potential of bias of classification, of course. This is why we need to understand.
I mean, this is some. This is some postdoc talking, right?
Okay. Can you repeat? Okay. Then let's go on. This is why we need to understand which factors are influencing the internal concentrations to improve such assessments. That's the point where I come to the overview and the research question of this work. So the main overall question is, how do internal concentrations and biotransformation improve the mode of action classification compared to traditional external concentration related approaches? Then another important question is, how do uptake and biotransformation shape the internal concentrations and toxicity in the zebrafish embryo? And how does chemical structure shape the uptake, biotransformation, and toxicity in the zebrafish embryo? And now I come to the first part of the results part, which ended up in a publication from 2024, addressing the question, how does biotransformation and internal concentration improve the mode of action classification of compounds? And on this slide, I would like to give you an overview on the workflow of how we prioritize chemicals with potential specific toxicokinetic behavior. So at this study, we typically began with a simple comparison. We compared modeled internal concentrations only, which were only predicted based on physical chemical properties, but ignoring biological processes like biotransformation or specific transporter activities. And on the other hand, we compared these data to really experimentally determined internal concentrations to see if there are deviations. And if there are no deviations, we can likely conclude that the internal concentration of these compounds is likely shaped by passive uptake, which is mainly shaped by physicochemical properties. And if we have substantial disagreement between these data, we have a potential impact of specific toxicokinetic processes on the internal concentrations, like biotransformation or transport activities. And this study was conducted initially for 63 chemicals, including pesticides, pharmaceuticals, and industry chemicals. However, in the scope of the PrecisionTox project, this chemical list was enlarged up to 138 compounds, which were experimentally tested by us. First of all, I come more to details of the methods. So on this slide, I show you the predictive approach, how we predict the internal concentrations. So this slide illustrates the principle of the mass balance model we used. And the model assumes a mass balance between the external medium and the internal aqueous concentration of the embryo, which means that at the steady state of the internal concentration, the external concentration equals the internal freely dissolved concentration. And after the uptake of the compound into the embryo, we assumed that there are three main compartments. The largest compartment is the aqueous phase, and the most sorbed phase we assume were the protein phase and, of course, the lipid phase. And there's a strong assumption for this model, namely that there's a steady state of internal concentration, and it's only based on passive uptake, which makes it a very effective screening tool to screen chemicals which are really reaching the steady state, or chemicals which are likely not reaching steady state of internal concentration. And important parameters for this mass balance model are, of course, body mass parameters describing these three main fractions, namely the fractions of the aqueous, protein, and lipid phase, and on the other hand, physical chemical properties of the compound describing the distribution of the compound into these different fractions, namely the acidity constant, pKa, the molecular weight, and the hydrophobicity, which is described by the log-D value. And on the other hand, on this slide, I show you the workflow, how we experimentally determine the internal concentrations and also the extracts used for metabolic analysis. And this was typically conducted during a 96-hour exposure experiment. During this 96-hour of exposure, both exposure media and zebrafish embryos were collected in triplicates, and these embryos were homogenized using a methanolic extraction protocol using fast prep homogenization, and the resulting extracts were analyzed via targeted quantification using LCMS, using a triple quadrupole for quantification of internal and external chemical concentrations. And on the other hand, we performed UPLC high-resolution mass spectrometry using UPLC Q-TOF, MS for non-targeted screening and transformation product identification. Now I come to the first step of the results. So on this slide, you can see a kind of quality control where we compared the expected nominal concentration in the medium versus the really measured concentration in the medium. And you can see that the external concentrations are closely matched to nominal concentrations across all analytes, except two outliers showing stronger deviations between both values. For example, the aminophenol showing 7-fold higher concentration than expected, and atorvastatin showing a 0. or a 10-fold lower concentration than expected. So this indicates that the concentrations, for all replicates, the concentrations were more or less in the expected range. And now we come from external to internal concentrations. So on this slide, you can see on the direct comparison between mass balance model predicted values and the experimental ones. On the x-axis, you can see the predicted concentrations, and on the y-axis, the experimental one. And what you can see is that for most of the chemicals, namely 80%, predictions are very close to the measurements, namely in one order of magnitude. However, you can see also compounds, 14 compounds, showing more than a factor of 10 deviations to the prediction. And for these chemicals, we can expect some kind of deviation in the toxicokinetic behavior. And this chemical set was supported by another chemical set, which was not published, but this was recorded in the overall PrecisionTox project for 138 compounds. And then you can see indeed that the majority of the compounds or the internal concentrations of the majority of the compounds are nicely matching to the predicted ones. And the next step was we wanted to explain the deviations between the model and the prediction, because these point to an impact of biological processes such as uptake kinetics and biotransformation. On this slide, I selected two representative compounds to show you the impact of the uptake kinetics. On this slide, I show you genistein and niflumic acid sharing both similar molecular weights, and they are both mainly negatively charged at the pH of 7.4. Sharing also similar values of hydrophobicity. So based on these physicochemical properties, we would actually expect that they show a similar uptake behavior into the embryo. However, they show very different uptake profiles. If we look on the orange curve, which is the internal concentration during a stable exposure concentration, which is indicated in blue, you can see a delayed uptake for genistein up to 48 hours of exposure, and then a rapid increase up to 10-fold higher internal concentration compared to the external concentration. And if you go down to the niflumic acid, this shows near linear uptake and remains close to external concentration, and it's not really reaching a steady state. And yeah, based on this data, we can say if slow uptake would be the only issue, both chemicals would more or less show similar levels over the time. But here, genistein keeps building up while niflumic acid only increases a little or stays much slower. And this could indicate an impact of transformation or transporter activities. So we look more detail what happens to these compounds when they reach the inside of the embryo. And to study this in more detail, we investigated the biotransformation of these compounds. What you can see here is the relative amount of the parent compound and its transformation products by comparing their peak areas. And to minimize ionization bias, we analyzed data both positive and negative ionization modes. And this allows us to identify dominant transformation pathways rather than absolute concentrations. And what you can see is on the y-axis the relationship between the peak area of the individual compounds to the total peak area. And what you can see is for example, nucleic acid, it seems that the glucuronic acid or the glucuronide metabolite seems to be dominant across this transformation profile. And this is also the case for genistein, beside several other metabolic degradation products. And yeah, for both compounds, we detected broad range of transformation products, and the large fraction of the total peak areas associated with transformation products. And this indicates a potential role of biotransformation in this prediction measurement discrepancies. And now I want to translate these findings into what we actually want to make, namely a mode of action assessment of the compounds. So on the left, you can see the traditional assessment only based on external concentrations, and this is basically plotting the SC50 values against hydrophobicity, and the solid line indicates the baseline toxicity cues for the zebrafish embryo. The gray area indicates the factor of 10 deviations to the QSAR, and every point which is inside this gray area is classified as baseline toxicant, while the points or compounds which are outside this range are classified as specifically acting compounds. However, if we translate this to internal concentrations, namely to the internal membrane concentrations, which are basically internal concentrations normalized to the lipid content of the embryo, there you can see a different picture, because these red marked compounds are classified as baseline toxicants if we consider external concentrations. However, if we go to internal concentrations, they are classified as specific acting ones. And yeah, this demonstrates the importance to consider internal concentrations when we speak about mode of action classifications, because only looking at external concentrations could actually hide really relevant information of such compounds. And the next question was, how can we actually try or connect internal concentrations and biotransformation to the chemical structure of compounds? And this ends up to the next study where we want to answer the question, how does chemical structure shape uptake and biotransformation and toxicity in a zebrafish embryo? And for this purpose, we selected a structural related series of electrophilic acrylamides because they share a common Michael acceptor reactivity center, which ensures consistent reactive mode of action. And by varying the N substitution by alkyl or aromatic substituents, we could vary the hydrophobicity of the compound. And yeah, hydrophobicity is both determining the uptake and also the toxicity of compound. And this enables us to link the chemical structure to biotransformation, uptake, and toxicity. Yes, on this slide, we compared data on hydrophobicity, reactivity, and how they influence the toxicity. And first of all, we compared the observed SC50 values for these compounds in zebrafish embryo to their reactivity to the biological nucleophile glutathione. And actually, because of their electrophilic reactivity, we expected a relationship between the toxicity and the reactivity, but you can see that there's no apparent trend. And this is kind of interesting because in a previous study by Hochthausen et al., we indeed observed a correlation between toxicity and the reactivity. However, if we compare the toxicity or if we relate the toxicity to hydrophobicity, then we see a trend between toxicity and hydrophobicity. And if we combine both in a multiple linear regression, we can see actually a nice match between the prediction by this linear regression and the experimental values, meaning that the combination of hydrophobicity and the reactivity of these compounds shape the observed toxicity in a zebrafish embryo. What's about the impact of internal concentration of this? So actually, we would expect that compounds with a stronger hydrophobicity also accumulate stronger inside the embryo. So we would also expect that compounds showing higher internal concentrations are also more toxic. And if we relate the relative internal concentration to hydrophobicity, we can see indeed internal concentration is important for this compound. And if we translate the internal concentration, or if we relate the internal concentration to toxicity, we can also see that this is also related to each other. And we also found out that the end substitution patterns determined the activated transformation pathways. And for this purpose, we analyzed the metabolic profiles of these compounds. And interestingly, acrylamide and bisacrylamide showing, which are not substituted to acylic or aromatic change, or aromatic substituents showed only glutathione-related transformation, while further substituted compounds showed additional transformation pathways like taurine conjugation or also glucuronidation and sulfation. But interestingly, the shared or the many shared transformation pathway includes the glutathione and mercapturic acid conjugation. And the hypothesis based on this data is basically that glutathione-related biotransformation can be influenced by the end substitution. And this is why we wanted to relate, or why we wanted to understand the importance of these transformation pathway, both to hydrophobicity and toxicity. And if we can see, or if you can see here, I plotted the importance of this transformation pathway to the hydrophobicity. What you can see is actually that very hydrophobic compounds show lower importance of this glutathione-related biotransformation compared to highly polar compounds. And we can also see that the more toxic compounds are also less dependent on this or less activating this glutathione-related transformation pathway. And taken together, chemical structure shape both uptake through the hydrophobicity and also controls pathway preference in biotransformation. And together, these processes determine the internal concentration and the resulting toxicity in a zebrafish embryo. And bring me up to the conclusions of this talk. So conclusions are zebrafish embryos are suitable model for predicting chemical toxicity based on both external and internal concentrations. And internal concentrations are largely predictable, but internal concentrations are important to avoid misclassifications. Biotransformation modulates internal concentrations and the toxicity. And the translation relevance of biotransformation, or it has a translation relevance well, there is a translation relevance of biotransformation in the zebrafish embryo, also to other species. And the internal concentration improves the mode of action classification compared to only relying on external concentrations. And future perspectives are to improve the predictive power of internal exposure, a total quantification of transformation products is required to make more stronger quantitative conclusions on the internal exposure of transformation products, and also to establish mass balance. And also the characterization of distribution and elimination kinetics would further strengthen the mechanistic insights of toxicokinetics of compounds in the zebrafish embryo. Studies on cross-species extrapolations are important, and also the improvement of throughput of such internal concentration tests are really important to translate this from research into regulative use. And last but not least, this research is a step forward to integrate internal concentrations into risk assessment. And last but not least, I would thank all collaborators to this work. The group for organic trace analysis of the environmental analytical chemistry department of UFZ, then from the ecotoxicology department, Stefan Scholz and Ricardo Massaya from the PrecisionTox consortium, and also from the cell tox department, Beate Escher and Julia Hochthausen. And I would also thank to all collaborators from the PrecisionTox project. And thanks for your attention.
Thank you very much, Nico, for this great overview about internal concentration analysis in zebrafish, in the zebrafish embryo model. And yeah, we have time for a discussion. So please raise your hand or speak up for any questions. Okay, it might be that I don't see the raised hand, so if I don't call you, then please.
One.
You see someone?
Yes.
I don't see any hands.
How can I?
Hi, can you hear me?
Yeah.
Now I see it. Yeah, Kehinde.
Yes.
Please go ahead.
All right. Thanks, Nico, for the clear presentation. I have a question. I was wondering, what's the vessel you use for your experiment? Is it a plastic vessel or a glass vessel?
This is strongly related to the physical chemical properties of the compound. So we performed initial screening of the physical chemical property data to select the suitable vessel for experimental exposure. For example, for more polar ones, I performed the exposure in 96 well plates, plastic plates, and for more hydrophobic ones, the exposure was conducted in glass to avoid sorption to the plastic surface. So it was like a mix of suitable vessels.
Okay, well, interesting. That's good to know, because I was wondering that the choice of vessel will impact the optic kinetics. And it makes sense if you use glass vessels for the hydrophobic one, then you don't expect any absorption. You don't expect any absorption. So then you did the mass balance based on the external. And okay, good. Thanks.
You're welcome.
One important information is also that in the PrecisionTox project, by purpose, we try to avoid very hydrophobic compounds. So typically the cutoff value was like around 4 to 5. this was not because we think that these other compounds are not relevant, but we wanted to test many chemicals, and the idea was we avoid chemicals for which we would have needed very special exposure protocols like repeated exposure or even maybe passive doses and so on. So yeah, that's why we were here in line with also had a very good match of the nominal and the exposure concentration, but principally you can do this also with more hydrophobic compounds, but then you have to apply certain measures to keep the concentration stable.
Yeah, and also one important point is to check if the compounds are absorbing to the surface of the embryo, especially for hydrophobic compounds. So for each hydrophobic compounds, we performed initial test like short time exposure, like 1 minute, which is expected, showing no significant uptake. And after the washing procedure, we analyzed the concentration in the extract to check potential bias by adsorption to the surface. So this was another quality control aspect of our work.
Okay, that makes sense. Do you also consider volatility of compounds?
No, but this was also considered in the selection of compounds. So we didn't test volatile compounds because it doesn't make sense to test them in this setting.
Yeah, thank you.
You can do it, but then you need to use kind of closed vessels and so on, and make it's possible. But we didn't. The goal of the project was not to develop protocols for difficult compounds. So that was not the goal. So that we avoid. That's why that was the reason why we avoided this compound.
Okay.
Are there more questions? No more questions.
Doesn't seem so.
I don't know if we might have questions in the chat. I don't know. I can check. No, there's nothing in the chat.
Didn't see anything?
No,
okay.
The chat is empty. Okay, so if there are no more questions, that's the final call. I think we can convene, and if you have more questions later, please feel free to get back to Nico and me and ask further questions. I don't know. There's one. John wants to say something.
Yes.
Go ahead.
Yes.
Thank you. I just wanted to say thank you both for such a wonderful seminar and for sharing with the whole community the work that you've done over the last 4 years, especially Nico, who ended up being granted a well-deserved PhD from this work. So thank you both.
Okay, thanks, John, for the warm words. And maybe, Monica, do you want to say some concluding remarks or announcing next? There's another question from Kehinder. Please go ahead.
Yeah, thank you. Just occurred to me now. I was wondering about the criteria for choosing the concentrations.
You mean the exposure?
Yeah, the exposure concentrations.
I think. Yeah, Nico, you can.
Are they like toxic concentrations or below toxic concentrations?
So this was actually a combination of baseline toxicity predictions and also experimental SE50 data. So for the toxicokinetic assessments, I typically used non-toxic concentrations to avoid any bias by toxicity. And therefore, I used concentrations well below the concentration where we observe any toxicity. And this was typically 10 to 100 fold lower concentration than the LC50. No.
Okay, thank you. Because I was just like, if I remember again, the slide where you had this genistein chemical, so it's like up to 80 micromolar. And because I know, like, typically in biotransformation experiment, it's, well, like you said, also less than it's usually non-toxic concentration, and most time it's usually around 0.01 micromolar, just to be super safe. So it's just well, I think I saw about 60 micromolar, and that's why I asked that's a question.
Okay. Yeah, as I said, we selected this more or less data driven. So we checked individually which concentration is suitable for each individual compound.
I mean, another aspect, if I remember correctly, Nico, was also the detection limit, right? If we would go for very low concentration with this small model, it's not that we have huge amount of tissues. We used like up to 10 embryos or so, then it's also with lower concentrations, you are kind of limited with what you can detect.
Exactly.
Yeah.
I mean this actually works for the parental compounds. So our analytical method is actually quite sensitive. However, this might be not really the case for the transformation products. So we don't know the sensitivity of the transformation products, and to capture as much as possible, we would of course like to go not that low with the concentration. Yeah.
Thank you.
Okay, so I think we